So here's an example question about solving a maximum power transfer problem. So we have here the circuit for a source, and you can see there's a fair bit going on inside of that, but that's going to be the source of energy. And what we're trying to do is maximize the amount of power that we deliver to our load, which is our resistance R, through our terminals A and B here. So the part A of the question is find the value of R that delivers maximum power. So in order to do that, remember the condition of maximum power transfer is load resistance equals the Thevenin resistance of our source. So that will be how we solve part A. And then part B says, well, once you know the condition, well then how much power do you actually deliver? And so that will be straightforward sort of voltage divider and power analysis question. So our strategy is to calculate the Thevenin equivalent. So strategy, calculate the Thevenin equivalent of the source. So we need to know the open circuit voltage in order to get the Thevenin voltage. So to analyze the open circuit voltage, what I'm going to do is redraw my circuit and solve for the condition where there's basically nothing connected across the output. So solve for VOC, the open circuit voltage. So I'm going to disconnect the output here, just leave that one floating, and the voltage that I am interested in is this voltage or this node labeled VOC here with respect to ground, which will be, I'm going to label on the bottom there. So this voltage VOC, or the node VOC with respect to ground, is the open circuit voltage of my circuit. And I need to analyze this. I'm going to use the node voltage method. You could use mesh current if you wish. Doesn't matter. I'm going to label V1 and V2 as these other essential nodes in my circuit. Now here, VOC is not actually an essential node, right? There's only two branches. But because this is the voltage that I'm interested in, I'm still going to include it in my system of equations when I write Kirchhoff's current law. Another thing that I can see straight away from looking at this circuit with a reference node here and a source that connects directly to the reference node, it's obvious that the voltage V1 over here is 100 volts. So it is 100 volts higher than the reference, so V1 is trivially known. And I also have a dependent source, which depends upon the voltage through a voltage across this 4 ohm resistor. And expressed in terms of my node voltages, this V phi is going to be node voltage V2 minus 20. So there's a 20 volt source on the bottom side of that V plus, and that connects directly to ground. So clearly the point in here is at 20 volts with reference to my reference node, and so V phi is V2 minus 20. So with all that information in hand, I can go ahead and analyze this circuit. So if I do Kirchhoff's current law at the node which is labeled V1, then here's what I will get. Actually, no, I don't need to do KCL at V1. I already know the voltage of that, so I'm going to do KCL at the node labeled V2. I don't do KCL here because I already know this voltage, and also doing KCL at that node would be difficult because I don't know the current through this 100 volt source, so that's why we learned all about supernodes, but I don't need that for this circuit. In this case, it's simple because V1 connects directly to the reference node. So KCL at V2, let's write that down. So to the left, the current through that branch is V2 minus V1 divided by 4 ohms. To the bottom, the current leaving is V2 minus 20 divided by 4, and then to the right, the current is V2 minus VOC, all divided by 4, and that is equal to 0. We can simplify this, multiply both sides by 4. That will get rid of all of these denominators. So that's V2 minus V1 plus V2 minus 20 plus V2 minus VOC is equal to 0. 4 times 0 will still give me 0. And then we can substitute in, we already know a value for V1, that's 100 volts, so I'm going to sub that in right away. So putting the 100 volts in and collecting like terms, so I will get, from the V1, I'm going to get minus 100 here, and then from the V2s, I see 3 of them, so that will be plus 3 V2 minus VOC minus 20 is equal to 0. Which gives me 3 V2 minus VOC is equal to 120, just bringing my numbers to the other side. And VOC is the parameter that I'm trying to solve for, so I'm going to prepare this so that I can substitute it into my next equation. I'm going to solve for V2. So I have the following, 120 plus VOC, which means V2 is 120 plus VOC all divided by 3. And that I'm going to call equation number 1. The next piece of information that I need is obtained by doing KCL at one of my other nodes. So I'm going to choose the point that I've labeled here as VOC and write KCL around that point. Now, one thing that I'm going to need to be careful of is when I write the current that's heading through this branch here, I just need to pay attention to what is the voltage on the left-hand side of that resistor. So what is the voltage here? So the voltage there, basically I can follow the sources. So I can start at my reference node and I can run all the way up. So I gain 100 volts to here, and then I gain V phi to get to that point. So it is 100 volts plus V phi to get to there. So let's actually include that in our equation. So KCL at node VOC is going to be that branch leaving across the top there. I can't quite fit it all on my screen, but it's going to be VOC minus that voltage that we just spoke about. So that was 100 plus V phi. So the voltage on the other side of that resistor is 100 plus V phi. And the resistor is 4 ohms. So that was one of my branches. And then my other branch is heading to the left. So it's VOC minus V2 also divided by 4 ohms, and that's equal to 0. Okay, let's simplify this equation. Again, multiply out the denominators of 4, and I will get the following. So I'm just going to expand these brackets. 100 minus V phi plus VOC minus V2 is equal to 0. Now I have a value for V phi, so V phi is V2 minus 20, so I'm going to substitute that in and collect some like terms. So I have 2 VOC minus 100 minus, and my V phi was V2 minus 20, so V2 minus 20, just use brackets, pay attention to your minus signs, minus V2 is equal to 0. I'm just checking I haven't missed a term here. So I've got my 2 VOCs, I've got my minus 100, my minus V phi, and my V2. Okay, looking good so far. We can further simplify this. So I'm going to expand these brackets and collect some like terms. So 2 VOC minus 100 minus V2 plus 20 minus V2, so just be careful of the negative signs there, and bring together my numbers and bring together my expression for V2s. So this gives me 2 VOC minus 80 minus 2 V2 is equal to 0. And now I can substitute my equation number 1. So substitute this one in for V2. So substitute equation 1. And here's what I will get. So that's 2 VOC minus 80 minus 2 times 120 plus VOC all divided by 3 is equal to 0. And we're pretty much there. So I just need to expand some terms here. So let's expand these brackets and simplify this. So 2 VOC. The constants here are going to be a negative 80, so I'm just getting my calculator. Negative 80 minus 2 times 120 divide 3. So that's going to be minus 160. That's the constant terms. And then I will have minus 2/3 VOC is equal to 0. So this is 2 minus 2/3 VOC is equal to 160. So VOC, we can just type this into our calculator. VOC is 160 divided by 2 minus 2/3, which is 120 volts. Okay, so this is the first part of finding our Thevenin equivalent circuit. So we know the open circuit voltage of this admittedly quite complicated circuit. The next thing that I need to know is what's the Thevenin resistance. So a few strategies, right? You could find the short circuit current and then use Ohm's law, or you could use one of the shortcut methods that we spoke about in a previous video, and that's what I'm going to use here. So find R Thevenin. Here's what I do. I turn off all independent sources. Okay, so let's have a look at that. I'm just going to change the label here. This is no longer VOC, that node there. So let's actually just call it V3 instead. I'm going to turn off all of my independent sources. So when you have a voltage source, you set it to 0 volts. So 0 volts means short circuit, means that no potential difference between those points. So this becomes just a short. And same thing for the 20 volt independent source here. So I'm just going to rub that one out and replace it with a short circuit. But I cannot turn off my dependent source. So for that one, I have to leave it as is. So I turn off all my independent sources, then apply a test source. Then apply a test source. So in this case, I'm going to choose a current source. So we're just going to connect a little current source here. Let's call this IT for test current. And then I'd like to know what is the voltage across my terminal. So what is my voltage V3? Once I know my voltage V3, then I can calculate the Thevenin resistance of this system. So studying this circuit a little bit more, I see my reference node is now directly shorted through to V1. So V1 is actually 0, so I don't need to try and solve for any voltage V1. That's actually the reference node. Then anything else I can do? I can write down my value for V phi. So V phi in this case is actually just equal to V2, right? Because it is now directly connected to that reference node. That 4 ohm resistor is now connected to the reference node. So V phi is equal to V2. Okay, let's go ahead and analyze this circuit. So I will have Kirchhoff's current law at node V2. I have to the left branch, remember that's the reference node on the left hand side there, so this is current leaving is just V2 divided by 4. Then down the bottom, the branch heading down the page, that is also V2 over 4. And then the branch to the right is V2 minus V3 divided by 4, and that's equal to 0. We can simplify this one, again multiply out the denominators, and if I look at this, I have 1, 2, 3 terms in which V2 appears, so this is 3V2 minus V3 is equal to 0. The thing that I'm trying to solve for is V3, so I'm going to solve this equation for V2 so that I can eliminate it later. So V2 is V3 over 3, and that we're going to call equation 1. Next step is KCL at the node labeled V3. So here, the branch that goes to the left, the current leaving through that branch is V3 minus V2 divided by 4 ohms. The branch to the top is V3 minus, now the resistance, the voltage at this point. You see the reference node runs kind of all the way around to here, so the voltage is basically just due to that source, and that source is V5, but also V5 is V2, so I'm just going to sub that straight in, it's V2. So the voltage there is V2. That one is divided by 4 ohms, and then there is the current source, so the current source is entering this node V3, so I write it with a minus sign, so minus IT is equal to 0. We can simplify this one, so I'm going to multiply out the denominators, so this will give me V3 minus V2 plus V3 minus V2 minus 4IT is equal to 0. And collecting like terms here will give me 2V3 minus 2V2 minus 4IT is equal to 0. I can then substitute my equation 1 into here. So substitute equation 1, and if I do that, I will get 2V3 minus 2 times, so V2 is this, minus 4IT is equal to 0. I want to solve this for V3, so I'm going to collect my coefficients, so that will be 2 minus 2/3 V3 is equal to 4 times my test current, which means V3 is, I'm just going to use a calculator, so 4 divided by all of 2 minus 2/3 is just 3 times IT. All right, so therefore we have that our Thevenin resistance is going to be the voltage at the terminal. So let's look back at our circuit. Our voltage at the terminal, which is V3, divided by the test current, which is IT. So voltage at the terminal is this, we just solved for it, divided by our test current, which of course simplifies down to 3 ohms. So therefore we can draw the Thevenin equivalent of the source as the following. So there is a ideal source which has a voltage, remember, voltage of 120, voltage of 120 volts through a series resistance of 3 ohms. So that is our source. And then we can connect our load to that. And here is our resistance R for our load. This is now the simplified version of the circuit that we're trying to analyze. So I'm sure you agree this one's much nicer. So the condition of maximum power transfer, so we can answer our questions. So part A was, what is the value of R that will lead to maximum power transfer? So maximum power transfer occurs when R is 3 ohms, right? When the impedances are matched or resistances are matched. That's maximum power transfer. And then part B asks us, well, how much power actually is that? So for that, I need to know what is the voltage across my load. So let's label it here as the voltage across our load. So for this, voltage across our load is by voltage divider equation, it's R over 3 plus R. And we know that R is 3 ohms, so this is 120 times 3 over 3 plus 3. So let's calculate that. So 120 times 3 divided by 6 is 60 volts. So we have 60 volts there. By the way, as a shortcut, you could have recognized that if these two resistors are the same, then the voltage will be exactly half. So the shortcut would be 120 volts, half of that is 60. So I'm showing you the working here, sort of full rigorous way to approach it. So we know the voltage is 60 volts. So the power in the load is V squared over R. So that would be 60 squared divided by 3. So 60 squared divided 3 is 1,200 watts of power. And so that's our question. So to summarize how we approach this kind of thing, if you have a complicated source, such as this one, then it's basically a Thevenin equivalent circuit question. So you convert it to its Thevenin equivalent, and that's really the hard part. And once you have the Thevenin equivalent, then you've got a really nice, beautiful, simple circuit, which is quite easy to analyze. Condition of maximum power transfer says this resistance is equal to the Thevenin resistance of the source, and away you go.